We're going to pick up where we left off here, talking about the relationship or the temperature dependence of vapor pressure. This is a graph showing vapor pressure as a function of temperature, and we see that vapor pressure increases as the temperature increases. The boiling point is where the vapor pressure equals atmospheric pressure. And so we see diethyl ether, ethyl alcohol, water. Ethylene glycol's boiling point would be super high. We talked about all that. The reason I showed you that graph just now, yes?
Can you boil a metal?
Can you boil a metal? I think you probably could.
So you could have like gaseous gold?
Well, you can definitely get metals into the gas state.
So you could have gas gold. Gold gas.
Yeah.
Interesting.
Yes, you can. So the relationship of vapor pressure and temperature, we just looked at the graph. It's not linear, it's a curve. It's an exponential curve. And so this is the equation that describes it. The vapor pressure equals a constant beta times E raised to the power of negative delta H, the heat of vaporization, over RT. If we rearrange this, this is called the Clausius-Clapeyron equation. And this is in the form of a line, and so if we graph the data this way, we actually can get a straight line. So here we have y, and this is our slope, m. 1 over t is x, and natural log of beta is our intercept. So we graph the natural log of the vapor pressure on the y-axis, and 1 over the temperature in Kelvin on the x-axis. We get a straight line, and the slope is equal to negative heat of vaporization over R, the gas constant. Okay, any questions about that?
Let me hold there for a second. Copy down the phone.
Yeah. It's also in the book, but I know that's another step. You have to go look at the book. It's tedious and everything. I need background music. Just waiting for Seth to copy down the equation. Oh, you said you were good? I didn't hear you say that. You're still looking at the screen.
Quietly, so that way you didn't hear me, so I can keep going. That's not my excuse.
Okay. So here's an example of some real data. We graph natural log of P, the vapor pressure, as a function of 1 over T. The temperature is measured in kelvins. And so we get a line. And as is typical with real data, it's not perfectly straight, but we draw the best fit line. And then the slope here is determined as minus 3478 Kelvin. That is equal to negative delta H over R. And so we can rearrange that, and we can actually calculate the heat of vaporization from this graph. And so that's one use of the Clausius-Clapeyron equation. You can measure the vapor pressure and the temperature. And by graphing the data in this way, you can calculate the heat of vaporization. So this is a problem that we're going to talk about doing. I'm not actually going to do it in lecture because it involves, you got to graph it and stuff, and so that's hard. So the vapor pressure of carbon tetrachloride was measured as a function of the temperature, and the following results were obtained. So here's our data. It says determine the heat of vaporization of carbon tetrachloride. Well, this is the situation where you'd use the Clausius-Clapeyron equation. But you can't just graph temperature and vapor pressure. It needs to be the natural log of the vapor pressure. So we want natural log of vapor pressure. So what you would have to do is you'd have to take those pressures and take the natural log of them. So that's ln. So the natural log of 11.3, that would give us 2.4248. And so that you would do that for each of these and calculate the natural log. And then for the temperature, we need 1 over the temperature in Kelvin. So 1 divided by 255, its temperature is 0.003922. And the unit on that would be inverse Kelvin. And so you would do the calculation for each of those, and then you'd graph the data. So you'd make a graph, natural log of P versus 1 over T. And then you get a line with a negative slope. Then you use the Clausius-Clapeyron equation, and delta H, the heat of vaporization, which is what we're trying to calculate, is equal to the negative slope times R. Now, R is the ideal gas constant. It is a constant, but the actual number is different if you use different units. So the 8.314 joules per mole Kelvin is the one you're going to want there. Any questions about how you would go about doing that? Obviously, this is very involved to be solving on an exam. You know, you're not going to make you graph stuff on an exam. But if you were given a picture of the graph and you were given the equation, you should be able to do that, right? We can also express this equation in a 2-point form. And so this is useful for predicting vapor pressure at another temperature. So for a lot of things, we know what the heat of vaporization is because other people have been very busy calculating and determining all these things. And we can usually find a vapor pressure at some temperature, but it might not be the temperature that we want it at. And so we can use this equation if we know the heat of vaporization and the vapor pressure at one temperature. Then we can use the equation to calculate the vapor pressure at some other temperature that we're interested in. So it's the natural log of P2 over P1 equals negative heat of vaporization over R times 1 over T2 minus T1. So let's do an example. I'm going to just write down the equation here. So it's the natural log of P2 over P1 equals negative heat of vaporization over R times 1 over T2 minus 1 over T1. Propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? Well, let's identify what they're giving us here. So there are two temperatures, right? And we're trying to calculate vapor pressure at 25. I'm going to think ahead a little bit and choose my 1s and 2s just to make it easier. But if you choose backwards, it just makes the math a little trickier. You'll still get the correct answer. So I'm going to choose P2 to be the 25. I'm sorry, T2. So T2 is 25 degrees Celsius. We need to have these temperatures in kelvins. So we add 273.15 and we get 298.15 Kelvin. And I'm going to choose T1 to be the other temperature, which is minus 42 degrees Celsius. I'm not going to do this one in my head. Minus 42 plus 273. 273.15. 231.15. They gave us heat of vaporization. They didn't give us the vapor pressure at the minus 42. What's the relationship between boiling point and vapor pressure?
They're inversely
No.
Exponent or something. Okay.
So we're grasping at it. So as you heat a liquid up, its vapor pressure increases. It boils when the vapor pressure equals the atmospheric pressure. So at the normal boiling point, the vapor pressure is atmospheric pressure, or 1 atmosphere. So the fact that this says normal boiling point means that at minus 42 degrees Celsius, the vapor pressure is 1 atmosphere. Does that make sense? So T1, P1, so P1 is 1 atmosphere. And that would be an exact number, 1 atmosphere. So we're trying to find pressure 2. So let's plug these numbers into this equation and see what we come up with. So natural log of P2, that's what we're trying to find, over 1 atmosphere is equal to negative the heat of vaporization, so 19.04, write those units in there, kilojoules per mole, over 8.314 joules per mole Kelvin. You see a problem? We've got kilojoules and we've got joules, right? It doesn't matter which one we use, but they need to be the same. So I'm going to switch this one. I'm going to change that to joules. And I'm going to do it in kind of the cheaty way. Instead of writing kilo, I'm just going to write what kilo means, 10 to the third, and then that'll be joules per mole. It's the cheaty way, yeah. That's not proper scientific notation, but it gets the job done and requires minimal thinking. So I like that. And then we've got 1 over T2. So T2 is 298.15 Kelvin, and T1 is 231.15 Kelvin. So all I have on the right side is numbers, so I'm going to go ahead and do the math there. I've got negative 19.04 times 10 to the third divided by 8.314 times the quantity 1 over 298.15 minus 1 over 231.15, close parentheses, equals. So this equals 2.226399. That should be enough sig figs. What is P2 divided by 1? It's still P2. That's why I chose to make P1 the normal boiling point, because I knew that would happen and I just thought it would be easier. So now we've got the natural log of P2 equals this number, 2.226399. How do we get P2 by itself? So natural log is a function, right? So we can't divide by natural log because it's a function. We need to do the opposite function. When we use multiplying, we do the opposite by dividing. Adding, we do the opposite by subtracting. Here we need to do the opposite of natural log. The opposite of natural log is e to the x. So we take e to the x of both sides, and that gives us P2 equals e to the, 2.226399. And I get 9.26. On a problem like this, I don't really expect you to do a perfect job of significant figures. It's pretty messy. I mean, we've got this business going on over here, and we've got this. But I would say we shouldn't have more than 4 significant figures. And then we've got the issue with the logarithm. And so that's kind of a mess too. So this would have 4 sig figs there. I'd say at most 4. You guys have questions? Did I do something wrong?
If you were to switch T2 and T1,
Mm-hmm.
would you get a negative
If I switch these, then this would be negative.
would that would e to the negative that power? That'd be 1 over that?
Right. It'll end up working out the same, but the math
Okay,
is a little trickier.
Because T2 is associated with P2 and T1 is
Right.
Oh, okay,
Yeah.
Okay,
So if you switch these, then this will be negative, but then this is also switched, and so the inverse will take care of the negative. And if you didn't understand that, that's fine. Yes?
Where'd you get the 8.314?
Where did I get that 8.314? This is the other value of the ideal gas constant.
Oh, sorry.
That's okay, with units of joule per mole Kelvin.
All right.
I don't want to put liter atmospheres per mole Kelvin in there because the units won't work out.
That's the inverse log, right?
E to the x is inverse natural log, yes. And on a lot of calculators, those are on the same button, but you just have to do a function thing. And so that's kind of a clue for you too. 10 to the x is the opposite of natural, base 10 log. And e to the x is the opposite of natural log. So any questions? Is this a reasonable pressure? Do we expect the pressure, the vapor pressure of propane, to be higher at room temperature or lower than at minus 42? Higher. We expect it to be higher than it is. What would the unit on this be?
Four.
It would be whatever unit we used here. So here it'll be atmospheres. Okay? There was something I wanted to talk about that I think is of just kind of general interest. And I thought there was a better slide where it would come up, but it didn't. So I'm just going to run back here and look at this curve for water. So we talked about how when water starts to boil at 100 degrees, it doesn't matter how much heat you put in, it stays at 100 degrees Celsius until it quits boiling and it has all evaporated. And so the fact that water boils at 100 degrees Celsius limits how fast you can cook something with water. You can cook something a lot faster by deep frying it because oil has a higher boiling point. And so, well, it tastes good too, but the reason that food cooks faster in oil is because it's at a higher temperature. How do you get water to boil at a higher temperature?
Pressure.
You change the pressure. So we can get water to boil at 200 torr at only like 65 degrees. But if we increase the pressure above 1 atmosphere, the boiling point goes up. And that's the principle behind a pressure cooker. A pressure cooker is a pot with a lid on it and a valve, and the lid clamps on so that you can increase the pressure. That means you can boil your water at a temperature higher than 100 degrees Celsius, and the food will cook faster. So I just think that's kind of neat.
Do you cook with pressure cookers on?
I do not. I do not have a pressure cooker. We could make one. Pressure cookers are potentially dangerous. If the valve isn't good, the pressure builds up high enough and the lid can like blow off.
How would you lower the temperature without completely just letting it all out at once?
Well, I believe they have a valve that you can release the pressure without having it explode. Yeah. I don't know. I've never been in that much of a hurry. And honestly, my husband does most of the cooking. So I'm just like, yeah, he figures it out. He does awesome stuff. Okay, so what if we vaporize a liquid in a sealed container? We talked about, we showed the Erlenmeyer flask and we looked at the equilibrium. So it's a sealed container and we heat it So this is kind of like the pressure cooker. What if you keep heating it, right? And it's pressurized. It becomes pressurized. The temperature rises, the pressure rises. The gas then is going to become more dense. We get more and more gas in the same amount of space. The liquid becomes less dense. And at a certain point called the critical point, the gas and the liquid phases merge, and they become one phase called a supercritical fluid. And here's a picture of that happening. Here's the liquid and the gas. And as the temperature and the pressure increase, there comes a point where we just have one state. There's no meniscus. It's not a gas, but it's not a liquid either. It's a supercritical fluid, yeah.
Now, if you released and let out that pressure,
If you
would it
release the
immediately
pressure,
vaporize the liquid?
some of it would vaporize, and I think some of it would condense.
Okay.
Yeah.
If you were to just have pressure go up alone, but like start off with gas, increase that pressure, then smash the liquid.
Say that again?
In like a sealed container,
Mhm.
you have this gas.
Mm-hmm.
You just compress it with more of that gas. We would eventually turn back into a liquid, right?
You can take a container of just a pure gas, and if you apply enough pressure to it, you can get it to condense into the gas state. Yes.
Oh, with pressure.
I'm sorry, into the liquid state. It was a gas. So with pressure, you can get it to condense from a gas to a liquid. This situation happens at a particular temperature and pressure, and beyond that, you also have supercritical fluid.
Because with temperature rising, you get gas, right?
The temperature rising is what causes the gas pressure to build up and become more dense. And so you see the transition here. The gas is becoming more dense, more liquid-like. The liquid becomes less dense, more gas-like, and then they just kind of merge into one. That's one of those weird things that we don't observe much. Yes?
So it's kind of like the super cold liquids that we did last experiment where we had to introduce the crystal and that caused it to form the solid, but in the opposite direction.
That's a good question. Is it like a super cooled liquid? I don't think so. I don't think so, because the supercooled liquid is unstable at that temperature and pressure, right? You think impure thoughts about it, and sometimes it'll just freeze up on you. At this pressure and temperature, the supercritical fluid is stable.
Is it?
Yeah.
Okay.
Yeah.
I was thinking the only thing keeping it that way was the pressure.
Well, yes, but if you don't change the pressure, it's going to stay that way.
Okay.
With that liquid, we didn't change the pressure, right?
Mm-hmm.
And it froze on us.
Yeah. Okay.
And so it wasn't dependent on the temperature and pressure, it was just unstable. But there are some similarities.
Could you technically do this with water and freezing, since water expands when it freezes? Can you put enough pressure that the water won't freeze?
You can definitely change the melting point with pressure.
Mm-hmm.
Yeah.
But
But I don't think there's an analogous state between solid and liquid where it's kind of both and neither, like it is with the supercritical fluid.
Gotcha.
Supercritical fluids actually have some useful properties. They're very useful as solvents. One of the uses for supercritical CO2 is decaffeinating coffee. So to get the caffeine out of the coffee, you need a liquid, because caffeine is a large molecule and it's not going to be pulled out by a gas. But you don't want a whole bunch of solvents in there, you don't want residues left when you're done, and you don't want to take out the other good things about coffee. So they can use supercritical CO2 to remove the caffeine and not remove the flavor compounds, and then when you're done, the CO2 just evaporates and leaves no trace behind, and so you don't have any residues in your coffee, so that's kind of cool. So we have a a critical temperature and a critical pressure. And above that critical temperature, you can't have a liquid. And we'll look at some phase diagrams where we'll see that for a couple of different substances.